SwayamPrabha. Digital India. Educated India.
Welcome. So, we are in module 3. So, here we will learn weighted residual method and or weighted residual methods, and then we will first two lecture we will go through the weighted residual method, and then we will go for the finite element discretization of one dimensional problem. So, in this lecture I will cover mostly what is weighted residual method, and since we have already understood what is Rayleigh-Ridge or the weak form or the variational statement, then we will briefly discuss different weighted residual methods like Galerkin's formulation or Galerkin's method, and then Petrov-Galerkin method, least square method, and one of the other method I mentioned earlier is the collocation method. So, that I will also discuss in the process. So, let us first discuss what we have learned already. So, here first we have what we have learned. So, in a we learned what is weighted integral statement. So, weighted integral statement. So, from for any differential equation, for a differential equation or specifically the PDEs or partial differential equation. Now, in partial differential equation, we learn what is its weighted integral form or weighted integral statement. Then we learn that what is the weak statement or variational statement, the weak form, standard weak form, or the variational statement, that also we have learned. So, specifically simply this bilinear form, that is W and U equals to L of W. So, where W is essentially an weight function, a weight function, and U is the approximation for the field variable. So, we also learned something like this, that U is summation of Ci phi I. Phi I is a function of x. In case of 2D and 3D problem, it is a xyz. So, I is 1 to n and then phi 0. So, and the one important thing that we have learned is the weight function W is taken as phi, so or phi i's. So, so W is essentially a weight function. So, the weight function needs to satisfy some conditions actually. That also we have learned. So, what is the condition that needs to satisfy? That weight function needs to satisfy homogeneous boundary condition. So, W should satisfy homogeneous boundary condition. So, what is homogeneous boundary condition? That is 0, that is phi should be 0 at the boundary. So, now another phi should be 0 at the boundary where the field variable is specified, not for the Newman condition. So, in case of a Dirichlet boundary condition or the kinematic boundary condition, that phi should that weight function W should satisfy the homogeneous boundary condition. Because if you remember that our Brachistochrone problem, that is at this point, this is the curve. So, I can construct several such curves which is satisfying this two conditions. So, that is equivalent to the variation that we learned. So, this is the weight function is essentially the variation of this is a delta operator. So, delta of u. So, variation of u where the boundary condition specified, that is y 1 and y 2 in case of x y, right. So, this also we have learned. Now, so this is not true for the Neumann boundary condition where the derivatives of the field variable is specified, because Neumann boundary condition automatically arises in the weak form because of the integration by parts. That also we have seen. So, now another important thing we have seen that that if bilinear form is self-adjoint or the symmetric bilinear form, then we can easily construct its potential energy or the energy functional. So, that also we have learned, that is B of u comma u minus L of u. So, that also we have learned in the process. Now, one important thing is that here is that this symmetric bilinear form is not necessarily true for the all problems we will be dealing with, right. Now, in that case, it is not easy to construct this potential energy function, but it can be constructed. Now, if you look the weighted integral method or weak form of the variational statement of the PDE, then you can think of its a minimization of its potential energy given the potential function of this form, right. But now, so it's a minimization of the energy in that sense. Now, it is not necessary that you can always construct this energy or for given a problem. Now, in that case, the Rayleigh-Ridge that we have studied earlier, or the weighted integral statement of a differential equation, may not be always applicable to the all kinds of problems. In that case, a more generalization of the problem or more generalized approach is proposed, which is known as the weighted residual method. Even though the problem will be dealing with in this course, the weighted residual method, or popularly the most popular method of this weighted residual method is the Bubnov-Galerkin method, or the Galerkin approximation, is very similar to the Rayleigh-Ridge method that we will be studying. Now, the problem that we will be studying. Now, what is weighted integral method? Suppose there is a differential equation. I represent the differential equation in this form, say A of u equals to f. So, this is my differential equation with a boundary condition given with appropriate boundary condition. Now, this differential, so A is a differential operator. Now, if A is a linear differential operator, then again we can show that we can construct its energy function very easily, but A is not necessarily to be linear differential equation. Now, in that case, if A is my AU equals to F my differential equation, for such in case of a linear, if A is a linear operator, suppose A is d2 dx square is a linear thing, and when A is a non-linear, suppose d2 dx2 plus sine, when this kind of thing is there. So, this is non-linear. So, this is non-linear. So, now if I approximate, now suppose there is an approximation of the field variable, approximation of u. So, let us say u approx is defined as u. Now, let us say u tilde, okay, u approximation. Now, if I substitute this approximation to u in this differential equation, then what I will get is A of u tilde minus f, the quantity. Now, this quantity need not to be 0. When it will be 0? Because u tilde, when u tilde will be ux or u exact, then this quantity will be 0. So, then we define a residual of this quantity A u tilde minus f. This quantity is known as the residual. So, our objective is to make residual 0, so that my approximation is represented by the satisfy the differential equation. Now, to do that, what we can do, we can construct its weighted integral statement with respect to some basis function, so or the some weight function. So, now the weighted integral statement or weighted statement, I can write that integral of some function w, A of u tilde minus f into d omega, omega is the domain, this quantity I can write. Now, this weighted residual statement or the weighted integral statement is very similar to the what we have learned in Rayleigh-Ritz. So, now this quantity I want to make it 0. Now, look here that these w and u tilde both are function of x, right? Now, if the other way of looking this quantity, this integral statement or the weighted residual statement is the orthogonalization of the error. Why? Because this is equivalent to integral w of r is 0. So, r is the essentially error or the residual of the system. So, this error I am making or the orthogonalizing this error with respect to the weight function w. Now, this orthogonalization of the error means that I am pushing the, in a mathematical sense, I am pushing the error to the orthogonal to the solution space. So, what is orthogonality? Orthogonality of a two vector, we know, that is u of u dot v is 0, then we say that the two vectors are orthogonal. Now, similar to that, the orthogonality here is defined in terms of two functions which are w of x and r of x. So, integral of these two functions or the product of these two functions is 0. So, this is kind of the weighted residual method can be written as an error orthogonalization. whether if you look for the uh, Rayleigh-Ridge method or the weak statement of that PD, this is a kind of minimization, right? But both of them is actually same under certain conditions or under certain situations. Now, this error orthogonalization means it is also a minimization, but my solution space, which is essentially the approximation, it is dependent on the approximation of u, the error I push to its orthogonal base, so that error doesn't have any component on the solution space. Because what is the u dot v means? U dot v means there are two vectors which are perpendicular. So if this is u, this is v. So that means v doesn't have any component or any projections on u, cannot have, the projection is 0. So that's why we say the two vectors are orthogonal. So this concept here is very similar to this, that we try to make the error to the complement to its solution space. So that is the how we are constructing the solution space. Solution space is actually depending on the approximation, and how we are doing that? We are doing it with respect to some basis of the weight function which is w. Now this allows us to choose this w differently than Rayleigh-Ridge method. So w is a kind of more independent than the approximating function. If you remember, in case of a Rayleigh-Ridge method, that we choose the w which is phi I always. On the other hand, in the weighted residual method, we can choose w differently, and naturally this weight function need not to satisfy this homogeneous boundary condition where the Dirichlet boundary condition is specified. So this is one of the major generalization of the problem, and we can say that this is a generalization of the Rayleigh-Ridge method. So we remove the restriction of the weight function, or the restriction imposed on the weight function in the weighted residual technique. Now, I will describe some of the weighted residual method here. So one of such method is, suppose in case of a so let us take some the same thing when w of r dx, let us consider one dimensional case. So now my r is essentially a of u tilde minus f. Now u tilde I can choose like this, that is summation of j equals to 1 to n cj phi j. Now phi j's are function of x, and then phi 0. So we have explained what is phi 0. So phi 0, the it is required to satisfy, phi 0 is mainly due to the non-homogeneous Dirichlet boundary condition in the approximation. Now phi j, or the approximating function, phi j needs to satisfy what? Phi j has to, there are 2-3 conditions that we have mentioned earlier. So phi j must be complete polynomial. First, it should be complete polynomial. Now second thing that we require, that phi j should be such that that it will lead to a linearly independent stiffness matrix. So Bij, or B of phi I phi j should be linearly independent. Now this is again phi, here the weight function is chosen as phi I. So this is one of the condition. Now this condition will be now different here. Now here also that phi j should be complete polynomial, and phi j should satisfy the homogeneous boundary conditions, because the non-homogeneous part, or the phi 0 takes care the homogeneous or the non-homogeneous. So part. So phi j also will be homogeneous on the boundary. So now in case of a weighted residual method, let us choose W, which is psi I, so which is not equals to phi I. So now psi I is a different function. So now we remove that requirement that weight function needs to satisfy this homogeneous boundary condition at the boundary where the field variable is specified. So if I remove that equation, then this equation becomes, so now I will write psi I instead of phi I here. So now here I will write A of phi j. So this will be my phi j because u tilde I have approximated like this, and then I can write this as equals to integral psi j f of f so this is my dx equals to integral this is f into psi I dx, and the this term that will have this term due to this. So integral of psi I A of phi 0. So now if you look carefully that here this quantity, this function is different than this function. Now if you, the first thing that you will notice that if I substitute this quantity, then how it will look like. So this is nothing but integral psi I. So if I take this is a linear operator, so this will be my A of u tilde. I can write it as so let me write it in a different way. So this is summation A I j phi j, or let me not write it in this way. So this will lead to so if I write it in the this form phi j, so it will be given by this phi j A of, because it will have a generalization. So A of so let me write it phi j and Cj. So Cj I can write inside. So it is also a function of Cj, because Cj's are unknown coefficient for me. Now if this is a linear operator, that is A is a linear operator, then I can write this equation in this form. So A of Ij Cj equals to Fj, right, or sorry, Fi. So this Fi contains both. So here now if that means I just took Cj outside by substituting this equation. So in case of a linear equation, in case of a linear operator, linearly. Now this is a general form, so which is applicable for the nonlinear case also. Now here this if you look carefully, that depending on psi I, this Aij is whether it is, will show with an example that depending on psi I, this Aij will be symmetric or asymmetric or the non-symmetric. So if phi I and phi j, that means if phi's and psi's are same, then only it will guarantee a symmetric form. So this psi I, if it is a different thing, then it will not guarantee a symmetric form. Now, this is known as the Petrov-Galerkin method. Where this condition is true. So, this is known as the Petrov-Galerkin method. Now, if I take W, or this W is psi I equals to phi I, that is what we have taken from the Rayleigh-Ritz method. So, the same thing, that instead of psi I will have phi I here. So, now here A of phi j Cj dx will be equals to integral phi I f dx minus integral phi I A of phi 0 dx. Now, here will, if it is a linear, then Aij Cij or Aij Cj will be Fi. So, this in case of a linear A. So, this equation here Aij will be same. So, this is known as the standard Galerkin method or Galerkin's projection, sometimes known as Galerkin's projection or standard Bubnov-Galerkin's method. Now, what is the difference with the standard Rayleigh-Ritz method? Here you look, we have never done any integration by parts. Now, so if I write this, that is the phi I r of phi j Cj is my the general term is my, this is my the Bubnov-Galerkin method. Now, this is not Rayleigh-Ritz method, okay, because here we do not form, in case of a linear A, we get something like this. Now, here we do not form the integration by parts, or we do not achieve that through the integration by parts. So, the first thing that we can anticipate here, that the differentiability requirement which was which is required here will be order of higher order compared to Rayleigh-Ritz method. Now, why? Because in the Rayleigh-Ritz method, or the variational statement or the weak form, we transferred the differentiability into the weight function, and then that's how we reduce the differentiability requirement in the weight function. Now, in case of a Galerkin method, this process can also be performed if function allow us to do it, or the differential operator allow us to do it. I will show with an example that if the differentiability requirement can be reduced in Galerkin's formulation, and it can be transferred to the weight function. So, and then obviously the natural boundary condition will automatically arise. But here, if you look carefully, that both of these methods, the Petrov-Galerkin and the standard Bubnov-Galerkin, none of the natural boundary condition or any of the natural boundary condition is arising. While in the weak form, we notice that natural boundary condition automatically arise in the weak form or the Rayleigh-Ritz method. So, this is one of the major distinction, but this Galerkin method can be equivalent to the or same as the Rayleigh-Ritz method when there is no natural boundary condition, first of all. So all the problems are Dirichlet boundary condition. All the boundary conditions are Dirichlet boundary condition. Then Galerkin methods are equivalent to the Rayleigh-Rince method, and obviously you have to use the same approximating function. Now another important point here, that even though we remove the restriction of satisfying the weight function to be homogeneous at the boundary, our phi j's, the approximating function, that is this quantity, this condition has to satisfy this, means that at the boundary phi i's need to satisfy the homogeneous boundary condition. So that means in case of a Petrov-Galerkin method, we restrict this condition that it need not, the psi I need not satisfy the homogeneous boundary condition, but phi j's needs to satisfy homogeneous boundary condition to be at the boundary. So this is very much required thing in the Galerkin's formulation, or the weighted residual method, because otherwise the approximation will not be valid here. Now, so in a nutshell, that the Galerkin method or the Petrov-Galerkin method, what we mainly what is mainly different, the difference is this, that we remove the restriction on the weight functions. So and it's an error orthogonalization that I have already explained. So instead of if you look it in this way, that instead of minimization, which is a Rayleigh-Rince method. Now, so basically that in case of a, so this is standard Galerkin method. Now I will, in the next lecture, I will show with an example how these methods could be different in the for same or same differential equations. Now one more thing that we wanted to discuss is that actually based on this function, that is WR equals to 0, that weighted residual form, by taking different W we can arrive at different weighted residual method. For instance, if I take instead of if I take my W as del R by del Ci as my psi I, then I arrive the least square method. So this least square method is very similar to the problem that we have faced in the previous case. For instance, the if I take the same differential equation, a u tilde minus f is my R, then what least square method is that we minimize the square of the residual. So now if I take we minimize square of the residual. So this quantity I just wanted to minimize. So now to minimize this quantity, then what I do, I do integral del R by del Ci into R. This is the differentiation. So this quantity I make it 0. So this is the normal equation. So standard least square, if you do a problem that is Ax equals to B, that we all know is that it can be posed as a least square problem. So if you look, if there is a function lambda, scalar function, obviously I can pose it like this, that is Ax minus B transpose Ax minus B. So this can be, the normal equation will be del lambda by del x. X is a vector here, so which I can write as A transpose AX minus B. So this I make it to 0, which essentially A transpose AX equals to A transpose B. Now if there is A is a square matrix, so then I can and if it is inverse exists, then I can pre-multiply with A inverse transpose, and then I can get the AX equals to B equation. So it is solving AX equals to B is essentially solving this, but this is not true for the rectangular matrix. So now the same concept is applied here. So this derivative, and this is the derivative, and the R is the my residual. Now if I write, so this is very similar to this psi I R d omega equals to 0. Now that means that if I write it in the sense in case of this thing with U tilde, my U tilde is something like this, summation of j equals to 1 to n Cj phi j, j is a function of x plus phi 0. So if I substitute it here, then what I will get